Hi and welcome to MSc. In this video we're going to be looking at a stoichiometry problem, specifically one that requires you to determine the limiting reagent. So here's the problem we'll work through. We're trying to figure out what mass of the sodium nitrate will be produced when we react 1.25 grams of sodium phosphate with 1.5 grams of the calcium nitrate. So this is a double displacement reaction. You can see it down below. Okay, so let's start out by listing what we know, as we generally would. Again, what I like to do is above the reactants and products, I like to write the information that we already know. Instead of using subscripts with the pen here, I'm going to use square brackets, make my writing a little bit nicer than trying to squeeze it in as a subscript. But I know the mass of this, and that's the 1.25 grams. Here we have the mass of the calcium nitrate, and it is 1.50 grams. This is the mass we don't know over here that we're going to eventually try to figure out, the mass here of the sodium nitrate. And so I like to write that with a question mark. The other thing we can do, and you can show calculations for this or not, depending on your comfort level. I'm not going to here, but I'm going to say that the molar mass, and you can quickly do the molar mass calculations. So this is the molar mass of the sodium phosphate, 1.6394 grams per mole. Then for the calcium nitrate is 164.10 grams per mole, and the sodium nitrate works out to be 85 grams per mole. Excellent. So those are from the periodic table I'm working with. Always use the periodic table that your teacher provided for you. At this point, we can't just calculate this mass directly. We need to figure out which part of these, which ingredient, which reactant we'd run out of first. And we can't compare just the masses and say, well, I have more of this, so this one I'll have more of it left over. We have to compare a number of moles. So we're going to do 2 mole calculations here. And mole calculation that we'll do here is the moles of the sodium phosphate, which is then going to be the mass of the sodium phosphate divided by the molar mass of the sodium phosphate. Okay, I think it's good practice to label all the different pieces and not just have N and M's floating around because you have them some different places. This is a capital M, so sometimes my writing, especially with this pen, doesn't turn out great. But always check with your teacher what they'd like there in terms of the notation. Some teachers might say that if it's in that column, you might not need to identify it the same way, but I think it is good practice to do that, so I'll continue to do that here. The mass we have is 1.25, and the molar mass was 163.94. And when we do this, we will get a mole value of 7.624. 7 ... because I'm not rounding it yet, times 10 to the negative 3 mole. Okay, so that's part of it. The next one, we have to do it over here. And this is going to be the moles of the calcium nitrate. And it's going to equal the mass of the calcium nitrate divided by the molar mass of the calcium nitrate. Okay, and we had 1.5 grams divided by 164.1, and this gives me a value of 9.140767. ... Again, I'm not rounding, times 10 to the negative 3 mole. So at this point, you might say, well, again, this number is bigger, just like it was bigger up there. So this one has to be my limiting. I'll run out of it first, right? The problem here is that we can't make that conclusion yet. So I'm going to scroll down here, and I know that's going to hide part of the question. But we have to take into account the ratios that we're dealing with. And so how we'll do that here is we'll divide these numbers, the moles that we got, by the coefficients. And that will be able then to be able to compare which one is larger. Now there's some other ways to do this as well. And I would always encourage you to follow whatever your teacher suggests as a method on this, but this is how I'll show it. So what we're going to do is we're going to calculate a different mole value. And what I like to do, because I can't name two things the same thing and have them have different numbers. So even though I am still working with the moles here of the sodium phosphate, I'm actually going to call it mole prime. You can use a different notation if you want, but that's what I'll do here because it's a different value and I'm wanting to avoid more subscripts because this is already clunky enough as it is. And I'm dividing this by 2. So the reason I'm using the prime notation is just to delineate this as different than the value I got up here. That's how many moles I have in this. And so this is a different mole value that I'm calculating. So dividing this by 2, I get 3.8. 1, 2, 3, 7, times 10 to the negative 3, and of course it's still in moles. So we'll do the same thing on this side. So I'm going to use that prime notation again, and I'm going to calculate a calcium nitrate value that I'll be able to directly compare. And so we're going to take our original number of moles of the calcium nitrate that I calculated just above. We're going to divide this one by 3 because of the 3 out front. And when I take the 9.14 and divide by 3, I will get 3.0469 times 10 to the negative 3. So these two now can be directly compared. We're just looking for whatever one is larger is my excess, and the one with less is my limiting. So this one is less, and so therefore it's my limiting factor or limiting reagent. So it's the one that will run out first in the recipe. So it's the one that I'm going to use moving forward to calculate the mass of this unknown value of sodium nitrate. So we've really done the limiting reagent stuff at this stage. And if that's all you tuned in for, you're done. Good for you. Hopefully this has been helpful. Please consider subscribing and liking. But if you want to stick around, I'm going to then calculate the mass here to go over that part of the stoichiometry as well. I'm going to go to a fresh screen. I often encourage students at this point to kind of rewrite the equation with the information just that they need, to make a few less mistakes at that stage. And that's what I'm going to do here. You don't have to by any means. But one thing we want to remember is when we know that this is my limiting, this is the value here then that I'm going to use. So we're going to use this. And that's an important piece to remember. So here's the equation rewritten. And what we can add now is that we know that that's an excess, the sodium phosphate. We know the limiting now is the calcium nitrate. And we know that we're still looking for that mass of the sodium nitrate. We also now know the mole value here. And notice that this is the first mole value, not that prime different mole value that we compared. This is the first mole value that we calculated from the mass provided. That's important. We also know the molar mass of the sodium nitrate. So now we can actually get to the stoichiometry and we can set up a mole ratio here from the calcium nitrate over to the sodium nitrate. So we can write that the moles of the calcium nitrate to the moles of the sodium nitrate is 3 to 6, and that's from here and here. We might also notice then that this can be reduced. We don't have to work with the 3 and the 6. We can reduce it to a 1-to-2 ratio by noticing, hey, 3 divides into both of these. Now that's not an essential step, but it will make your math and a little bit of your work a little bit easier if you notice it. So watch out for those. We can then set up a fraction, and we can say, okay, well, the moles of this calcium nitrate divided by 1, because of this 1 here, is equal to the moles of the sodium nitrate divided by 2. I'm using the reduced. You could have also put a 3 over here and a 6 over here, and the math would work out the same. We're now going to solve for this one because that's what we're looking for. So opposite dividing by 2 is multiplying. And we don't really care about the dividing by 1. So I'm going to say here that the moles of the sodium nitrate equals 2 times the moles of the calcium nitrate. So this is 2 times the 9.1407 times 10 to the negative 3. And this is going to then equal 1.828 times 10 to the negative 2 mole. Now at this point, you can keep working down the page. I'm going to work in this blank area here to keep everything visible for you on the screen at the same time. And we're trying to calculate the mass here. I now know the number of moles I have of the sodium nitrate. It's this value here from the limiting reagent. And so I know my equation now for mass is the mass of the sodium nitrate is going to equal the moles of the sodium nitrate times the molar mass of the sodium nitrate. So this is going to be 1.828 times 85. And when we do this, we get 1.5539 ... And that's in grams now. This is where we have to worry about significant figures. So all the molar masses we used here were probably 4 significant figures. That's pretty standard with the exception of hydrogen on most periodic tables. But the numbers we were given, 1.25 and 1.50, were both 3 significant figures. So because we used 3 significant figures in our masses that we were provided, we're going to use 3 significant figures here, and that'll round to 1.55 grams. So the stoichiometry of this is on this screen. All the limiting reagent stuff we had to do prior. And notice that it didn't tell us in the question which one's the limiting reagent. It just gave you the information and you had to realize, oh, it didn't say anything about being in excess. I have to do a limiting reagent calculation and then I get to do my stoichiometry afterwards. I hope this run through of how to calculate a limiting and excess reagents and then how to do the stoichiometry that comes afterwards has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.